by a group of senior professional structural engineers from all over the country. IS Structi is registered under the Societies Registration Act 21 of 1860. IS Structi is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IAS Structi has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Kumar Ghosh, Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Alok Bhaumik, Shri Manoj Mittal and Professor R. Pradeep Kumar as its president. IAS Structi is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IAS Structi has collaboration with various international professional like-minded associations and institutions. IAS Structi's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IAS Structi endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IAS Structi is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IAS Structi's activities are widely appreciated and known for quality technical contents. IAS Structi is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines and a monthly newsletter. IAS Structi's publications are becoming popular with time. IAS Structi has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IAS Structi started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. IAS Structi is currently operating from 4 regional centers, namely Eastern, Western, Northern and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. IAS Structi has its student chapters in several leading engineering institutions as well. Membership of IAS Structi is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IA Struct E is available on its website www.iastruct.co.in.
Hello? Hello?
Yep. Yep.
My voice is audible?
Yes, sir. Voice is audible, but Dr. Bagchi is disconnected. I think there is some network issue.
Well, let's wait. He must be trying. Because I can just make a beginning, something.
Yes, sir. You can. You can.
Dear friends, today Dr. Ashutosh Bagchi, who is a leading professor and consultant in leading university in Canada, who has agreed to talk on current development in structural health monitoring of concrete structures. Dr. Ashutosh Bagchi, he was just there. There's some problem of connectivity.
Yeah, I'm sorry, I'm back now.
Okay, good. Professor Ashutosh Bagchi, we welcome you, and we are grateful to you for sparing your valuable time in sharing your experience. Before brief CV of Dr. Ashutosh Bagchi, I am going to say that he is a leading professional licensed engineer, fellow of the Canada Society of Civil Engineers, and professor of structures and infrastructure engineering in the development of building, civil and environment engineering at Concordia, University of Montreal, Canada. He served as the chair and head of the department in this university from 2017 to 2013. He is internationally recognized for experimental and analytical research in the areas of structural and monitoring, earthquake engineering, and smart structures. Dr. Bagchi is a recipient of Teaching Excellence Award of Concordia and a member of several professional societies. Now, brief of the topic. The topic is current development in structural health monitoring of concrete structures. The topic covers the current state of the art on structural health monitoring and its application to civil structures. The speaker shall discuss the degradation characteristics of concrete structures and related instrumentation and monitoring issues, data management, and condition assessments. Now, I request Dr. Ashutosh Bhakti to kindly proceed.
Thank you. So I'll share my presentation here. Okay. So can you see my screen?
Not yet.
Yes,
Not
sir.
yet.
It is coming, sir. It is coming.
It is coming.
Yes. Please make it in
Yes.
full.
Okay, I'll put in presentation mode. You can see
Yes.
it, right? Okay.
Yes. Yes.
So, all right. Thank you very much for inviting me to Indian Association of Structural Engineers um, lecture series. So as you know that I'm going to talk about current development in structural health monitoring of concrete infrastructure. So this is some views from Montreal. We are in summertime here, but in winter time, Montreal is snow covered. But in summertime, it's very beautiful. So I invite all of you to visit Montreal in summertime. So as you know, the current state of infrastructure around the world is not very good because many of the infrastructures, especially concrete structures, were built in 70s in developed world like North America and Europe. And many of them are in bad state because of the poor maintenance and degradation of those structures. In India, the situation is not that bad, but it is uh, getting there gradually because those infrastructures which were built around 20 years ago, they are in a shape which needs attention at this point of time. So as you know, like any other material, concrete degrades over time. Typically initial 10 to 15 years, there is not much of a problem. But then after that, the concrete structures gradually degrades because of corrosion of steel, the loss of strength in the concrete element, etc. There are many ways to represent that mathematically. This is one of the ways. So that's why sometimes it is important that we monitor these structures. Now, what is monitoring? Monitoring means we watch the structure for its behavior. It could be visual monitoring, which is normally done, like visual inspection, to look for cracks, look for any problems in the structures. But sometimes it does not capture the entire story because visual monitoring does not capture the internal defects in the structure. So that's why structural health monitoring through instrumental measurements or instrumental uh, assessment of the structural strength is important. The benefit could be manifold. It could lead to cost-effective maintenance, efficient repair, help in extension of service life, lowering the overall life cycle cost, and the better understanding of the behavior of the monitored structures. So if I take an analogy of the human body to structural health monitoring of infrastructure systems, if you go to a doctor, typically a doctor will feel the pulse, take the temperature, take the blood pressure, etc. Then based on that, we'll probably recommend some tests like maybe blood work, urine test, and things like that, and then do some prognosis and give a prescription that, well, based on these symptoms, based on these tests, these are the medication we need to take in order to rectify the situation or manage the situation. So similarly for structural engineer, we need to monitor the structure, means looking at the defects in the structure through visual monitoring, just like taking temperature. and the instrumental monitoring by looking through, say, ultrasonic test or ground penetrating radar, etc., or even vibration test to know what is going wrong with the structure. And then based on that, if the defect is excessive or deformation is excessive, then we prescribe some remedy. The prescription of remedy would maybe retrofit of the structure in different ways, and then the structure will perform at least for some time in a good shape. So typical use cases in the SHM systems could be providing an early warning system if there is a big problem in the structure, detecting anomalies, like the structure is expected to behave in certain ways. When there is a deviation from that behavior, this is called anomaly. So anomaly detection becomes easier when the structure is instrumented. Overall health assessment of the structure, monitoring the anomalies, the stress and strain behavior, and earthquake monitoring, data-driven decision making. Data-driven decision making means that when we look at the structure, we have a certain sense based on the structural engineering experience, but then instrumental measurement gives us insight so that helps us in the decision making in terms of the maintenance, retrofit, monitoring, etc. And forensic analysis. In case of any problem with the structure, if any incident happens, if it is instrumented, then instrumental measurements can give us some insight, just like the black box in a flight, okay, to assess the post-incident conditions. And overall, it helps in research and development. So there are many types of sensors we use normally to assess the structural response. It could be as simple as strain gauges and displacement sensors, or as sophisticated as fiber optic sensors, wireless sensors, etc. So what is important in this case is SHM system design. What is system design? It is to know what kind of sensors we need, what are the location of the sensors, what are the number of sensors we need, because we don't want to put sensors haphazardly and collect all kind of data which may not be very useful. Okay, so we need to design. There is a design component here. Okay, so sensor installation and placement is also very important, because if we don't place the sensors correctly, then we won't get what we want, right? So we need to track a certain behavior of the structure. So if we don't put the sensors in appropriate locations, we won't get that behavior. And then we need to have appropriate data acquisition system and data management system. So nowadays, many a time we rely on wireless transmission, which is easier, but sometimes we don't have enough data rate. So then we go with fiber optic sensing system. So when we collect data, we need to make sure the data is collected properly. We filter all the noise. We filter all the data which are not very useful, which are called mundane data, and then transfer and manage the data appropriately. And at the end, what is important is data interpretation and structural condition assessment. So many a times I see that the structures are instrumented, a lot of data is collected, but then there is not much done with that data. So data interpretation and assessment is very important. So measuring the signals and sent by installed signals for extracting meaningful information is very important here. Another important thing is data sampling. It is important to know what is the rate of data acquisition we need to track certain behavior. For example, if we want to just measure the temperature doesn't change every minute or every second. So we don't need to acquire the data very, frequently. We can probably measure the temperature once in an hour or something. But when we want to measure the vibration data, acceleration data, then maybe we need to measure the data maybe, uh, multiple times, maybe 32 or 64 times in a second. Okay. So this is called sampling rate. So if we don't sample the data in appropriate rate, sometimes we lose the data, we lose the information. And if we do the excessive data sampling, then that may not be useful either, because our data collection system gets clogged up very quickly. So based on the data, we identify the different stages of damage. So what are these stages? If the data tells us, if the data is just enough to let us know the structure has some problem, that is called level 1 detection. Level 1 means we just know that there is some problem with the structure. Okay. Level 2 detection is that we have enough sensors and enough data which tells us not only that the structure has some problem, it also tells us what could be the location of the problem. Okay, that is the second level. Third level is called severity of damage. That means the instrumentation needs to be more sophisticated. That will allow us to determine what is the degree of damage. And then once we know that, the hardest part is to assess the remaining service life. Okay, that means we know now that there is damage, we know the location, we know the amount of damage. Based on the location and amount of damage, we have to identify or assess what is the service life of the structure, how long the structure will be in service before it needs major retrofit and repair. Our goal here is to increase the service life through regular maintenance so that the overall life cycle cost reduces. Now, there are different kind of methods for monitoring a structure. There are local methods and there are global methods. Global methods are typically vibration-based damage identification, on-site continuous monitoring, load test of different kinds, static load test or dynamic load test. On the other hand, local methods are specific to different locations. If we have an idea that this location is problematic, we do acoustic emission test or magnetic resonance test or even X-ray or other electrical or geophysical method like GPR. So this is an example of structural health monitoring of a bridge. This bridge was, this is a special kind of construction they adopted for this bridge. It's called tide arch kind of system, where you see the deck, the bridge deck is resting on the bridge girder, 5 bridge girders. And these bridge girders are tied together by a steel strap. So, and the deck does not have any reinforcement, any steel reinforcement. So what happens if you apply load, the steel deck will crack, and because of the crack, it will push the girders away. But the steel strap connecting the girders will develop tension, and that will create an arching action in the concrete. And through the arching action, it will take the load. So this was an innovative approach where they avoided the internal steel reinforcements. Why? Because internal steel can corrode, and if corrosion is too high, then you have to replace the bridge deck. You cannot change the reinforcement, so you have to demolish and reconstruct. But in this case, it is external reinforcement. That means if the external reinforcement gets corroded, you can replace that easily. And since there is no internal reinforcement in concrete, the degradation in concrete is reduced. So this is in order to, because this was an experimental bridge, because that time the code did not permit this kind of construction, but they allowed engineers to build it if they could prove that it will perform similar or better than traditional construction, which is reinforced concrete construction. So that's why they needed to instrument it and regularly do the testing. So they did load testing and vibration testing. So based on vibration testing, we developed finite element models and updated the finite element models to make sure the mode shape and frequencies of this model correspond to the mode shape and frequencies that we measured in the fields. So these are mode shapes, and based on that, there are simulation studies were constructed. So typically it's shown how different damage detection technique could work. There is another example of a large dam in Quebec in Canada, which is largest multiple arch buttress dam in the world. So this dam was also, because of its unique construction, they wanted to monitor it regularly. So they did regular vibration tests and to track the changes, seasonal variation, as well as the variation from one season to another. So this is another example of a dam where we tried to simulate different damage condition and apply modal curvature based and modal strain energy based damage detection methods. So it says that modal strain energy can capture the damage appropriately, okay, but it's yet to be tested in the fields. So this is an interesting one where there is an arch dam where there is data available for few years of water level in the dam. So this is the flood water level, this is maximum operation level, and this is the minimum operation level. So that means water level varies among these levels. And when the water level is high, this dam crest is pushed higher. So you have tip displacement higher. Then if the water level is low, the crest displacement is lower. So this is one of the major parameters. The other parameters could be temperature changes. So if the temperature is high, then that can induce higher crest displacements. There could be seasonal variation, like in summertime, the displacement pattern could be something as compared to the winter time. So to capture all these things, there is a statistical model available, which is called hydrostatic season time model, or HST, which is based on multilinear regression. So basically, the displacement on the top of the dam is expressed as three components, one constant part and three components. First component depends on the water level. Second component depends on the seasonal variation. And the third component depends on the time where there is irreversible displacement or irreversible changes in the dam. So based on the available data, the HST model was developed and the coefficients were calculated based on a part of the data. Say, for example, if we use the 80% of the data from July or January 2011 to say January 2013, so that will be enough data to calculate all the coefficients of that multilinear regression model. And then rest of the data we calculate based on the input parameters. And then we calculate the displacement, compare with the available displacements. So we see that there is a good agreement between the model and the actual output. But what is important here is that from these three components, H, S, and T, if we plot their relative importance, we see that the blue line is basically the time component, the degradation with time, which shows that there is a steady degradation in the system or in the dam, but it is steady, nothing to be alarmed about. This is something to be expected, which shows that like any structure, dam also degrades in a gradual manner. The seasonal variation is seasonal, which stabilizes, and the other component does not have much effect. So that way, this model is very powerful. So there was another example. This is an embankment dam in British Columbia, where it shows that sometimes the predicted data or predicted output does not match the measured output. Okay, so what could be the reason for that? Maybe some of the parameters are not captured in the model, or some anomalies happen. For example, in this case, where we see that simulated data and measured data do not match very much, if we look at the other data, so it was stressed to the fact that there was a heavy snow melting at this period, so which was not captured in the inputs. So based on this, what we can say is that instrumentation and structural health monitoring provides an excellent opportunity for long-term monitoring of critical infrastructure like dams, bridges, etc. And vibration-based system identification, damage detection are cost-effective. Instrumentation of monitoring could represent only a fraction of overall cost and management budget. This is very important because sometimes the owner does not feel the need for instrumentation. Say, why do I unnecessarily put some money in that? But if we look at the investment there, investment is minimal. Okay, instrumentation doesn't cost much, monitoring doesn't cost much as compared to the overall management and inspection budgets. And if you look at the gain in life cycle cost, it is enormous. Okay, that's why there is no reason to shy away from it. So in most countries these days, all the special structures are now opted for structural health monitoring, especially for reinforced concrete structures, because there is a lot of uncertainties and a lot of variation there. So that's why any specialties we build in this kind of structure, they need to be monitored. Okay. And concrete, there is a lot of innovation happening in concrete. Like if you look at high strength concrete, different kind of admixtures we use in concrete, everything alters the performance of the material as well as performance of the structure. Sorry, I think there is some power surge here. You're seeing that the light is not proper. I think because of the the weather condition, there
But,
is,
it's okay. Please continue.
yeah.
There's
Okay.
no problem.
So the
Good.
other thing is that continuous and periodic monitoring could provide important data for risk-based failure mode analysis. Not only for dam, also for other infrastructure like bridges and buildings. Now, what is risk-based monitoring? So we know that a building, for example, are very susceptible to hazardous situations like earthquakes or high wind like tornadoes and all, right? So, so we design them for different levels of this earthquake. We need to figure out at these different levels of earthquakes, what are the probabilities of failure? So, and draw something called fragility curves, okay, which I'm not discussing here, but eventually that will tell us that at different levels of earthquakes, there is different level of losses that can be calculated, okay, or expected. Probability of different losses. And based on that, we can calculate the risk in the infrastructure corresponding to different level of hazard. Nowadays, we are moving from strength-based design to performance-based design and to resilience-based design. Resilience-based design means when an earthquake happens, or not just earthquake, any extreme situation happens, if the structures get excessively damaged, there could be life safety in the structure. That means structure will stand there. But because of the extensive damage in the structure and non-structural elements, the cost of repair could be too high. And that might not be expected, or that might not be useful. So that's why we need to build a system where the losses could be minimized. So this is called resilience-based design. So that also is tied to risk-based failure mode analysis. I think with this, I'll stop and encourage some questions from the audience.
Yes, I think that would be better.
Yeah.
Professor Bhakti, I mean, before I ask the people for questions, I have one or two small questions.
Yes, absolutely.
Number one, you said the data that you collect, the predicted one and the measured one, and if there is variation, how to know which data is reliable for our making decisions? This is question number one.
So yeah.
The second question is that for the healthy structures, we make a baseline signature.
Yeah.
And then the structure will degrade with respect to time. And the life of structure is, say, over 100 years. I mean, how to collect data and monitor it continuously for 100 years? What is the mechanism there in your country? These are my two small questions. Please
No,
reply.
I think these are two very important questions. So I'll go back to my example one here. If you look at this one, this bridge was tested several times. And this was newly constructed bridge in 1997. So when you do the measurement in 1997, you can take it as a baseline data and compare with other years. And then that provides you some idea in terms of comparison with the baseline. But many structures are not like this. You start monitoring in the middle of its service life. So the structure is already old, maybe it is 20 years or 30 years old already, and then you start monitoring, okay? So then you don't have the baseline data. So, but whenever you start that is somewhat baseline. Okay. This is one way. The other thing is when you do a data-driven analysis, that means you look at the data, just the data from any point of time, like here. So you look at the input, see cause and effect. So in this case, the water level, temperature, seasonal variation, these are the causes or parameters. This can be used as input. And the displacement at the top is the output, right? So you try
Right.
to relate the causes with the effect without the knowledge of the stiffness of the structure, mass of the structure, that is unknown. Okay. So you just try to relate the cause and effect that indirectly relates this through this stiffness mass, which is unknown. And then you plot their relationship. So this relationship can guide you through the behavior of the structure. So if there is any anomaly, that means if the input parameters are same, but suddenly the output parameter changes, suddenly the displacement changes compared to the input parameter, then you know something is wrong. So this is one way to interpret the data. So that's why when I said in few slides before here, maybe here, data interpretation is the most important part. Okay, because most of the structural health monitoring projects lack this data interpretation part. They put a lot of good sensors, sophisticated sensors. They collect good data, but data interpretation is usually basic. Okay, so I think structural engineers should put more attention to this. That is, I hope I answered your question.
All right. Thank you. I mean, Vikas, please read the other question.
Yeah, so there are few questions in the Q&A. Mr. Rahul Maru asked, how to model the structure that matches with the actual behavior? Which software was used?
Okay, so in this case, in this example, we developed our own software, but you can use any software like SAP 2000, Abacus or ANSYS to build the model. Okay. Modeling part is easy. If you have the structural drawings, you use the drawings to build the finite element model. But what is difficult is to match this structure with the actual structure in the field. What I mean by that is that when you do the field measurements of, say, vibration data, you extract the frequencies and mode shapes, and you build finite element model from the drawings, calculate the mode shape and frequencies. These two do not match, right? It may not match for several reasons. It may not match because of the discrepancies between the drawing and the construction. It may be because of the discrepancy between the assumed material properties and actual material properties. It may be because of the discrepancy in the idealized boundary condition and actual boundary conditions. So then you have to identify the parameters which could affect this performance or behavior of the structure. So boundary conditions, geometric details, and material properties. Okay. So this you have to fine tune. Now this fine tuning can be done manually, but if it is only few parameters, you can do manually. But for a large structure like this, it is not easy to do manual manipulation. So then we developed another technique called model updating technique. It is not that our technique, model updating technique exists in literature. So what we did, we studied different model updating technique and developed our own system to do an iterative model updating technique based on a process called matrix update method. Okay. So we applied that and then calculate the relative changes in different elements. Based on that, we developed the updated model, which matches the experimental model. Does that answer your question?
So
It's
thank
a
you,
long
sir.
answer.
Yes, sir. Yes, so Mr. Vinay Pandey asks, what should be the basis of deciding location of sensors?
Yes, that is a good question. It's part of the system design of SHM. As I said earlier, that we don't want to put the sensors haphazardly. We want to put them in the right locations. Now, what location would be right location? My experience shows that first you build the model of a structure. It doesn't have to be updated model, just a regular finite element model. And study its vibration patterns, study its displacement patterns due to different loads, and then identify what are the parameters you want to monitor. For example, in this bridge, maybe the mid-span displacement could be important. Maybe the different vibration modes could be important, right? So then if you are putting accelerometers somewhere, you need to put at the locations where you expect higher amplitude of vibration, okay? Not the points where there is not much of vibration, like nodal points, okay, or node points. Like if I say here, near the supports, there is no movement. So you don't want to put accelerometer there. But in mid spans or quarter spans, you put the accelerometers. If you want to measure the horizontal displacement at the column, top of the column, then you put some kind of displacement transducer there. Okay. So it depends on the type of instruments, type of quantity we measure, and that should be preceded by some kind of analysis, structural analysis to know the general behavior of the structure. All right.
Yes, sir. Yes. Thank you, sir. Mr. Uma Maheshwar Kusuma asked, what are the methods to monitor structural healthcare of healthcare buildings?
Okay. In healthcare buildings, there is, so they are called post-disaster building. Post-disaster building means they are expected to be functional after a major disaster like earthquake or any other kind of disaster. So to make sure in the design codes in any country, we'll have certain provisions to calculate the design loads. So that is one thing. The other thing is the protection of the non-structural elements, the machineries and components in the buildings. So for example, if there is an X-ray machine, which could be sensitive machine, right? So if there is excessive vibration, the machine could get damaged. So you need some kind of vibration isolation system for those machineries in order to protect them. Okay. And of course, you can monitor their vibration as well to make sure they are protected during this kind of movements.
Yeah. Thank you,
All
sir.
right. Yeah.
Yes. Miss Kinjal, I think asked, one second, sir. I am working at Gift City, a greenfield high-rise operational smart city. Is
Yeah.
it essential to install sensors during construction of the building for monitoring its structural health? If yes, what should be the essential building elements and where it should be installed?
Well, this is a very good question. I think construction time monitoring is if it is possible, then you should do it. Why? because construction time monitoring is very important to detect any kind of flaws that is happening during construction. Okay, so that you don't have to wait for later to find the fault in the structure and remedy them. Okay, and also sometimes designers make a lot of assumptions in designing a structure. While constructing, you can validate those kind of assumptions as we go. Because in construction, if you take an example of a multi-story building, if you do story-wise construction, which is a normal practice, the loads gets built up gradually, right? So that gives you an insight into any kind of stress built up, residual stresses, etc., as we go along. Okay, and also sometimes we depend on the we call it accelerated construction. Sometimes means we want to shorten the construction time. That's why we sometimes don't wait much in terms of concrete curing and etc. So that time monitoring is all the more essential to make sure that we have enough strength built up before we construct the next stage.
So thank you, sir.
I hope that
Yes, sir.
works. Yeah,
Yes.
thanks.
The another question from Kinjal is, what are the best methods to analyze structural health of building at 10 years or like 20 years of age of building where no sensors were installed during construction?
Yes, there are possibilities of having sensors internally and externally. So if you put the sensor internally during construction, that gives some advantage that you have the sensors right from the beginning, and also it is inside and protected, and you can get the periodic or continuous data. But for older structure, we don't have that luxury. So we can install the sensors externally. That is possible. And again, you first need to analyze the structure to know what are the important parameters you need to monitor, and what are the locations where these sensors to be installed. Okay.
Yes, sir. Yeah, yes, sir. The another question from Mr. Rishikesh Yadav is, in Indian Railways, when sensors are installed to measure line loads, there are significant vibration due to train movement. In such conditions, is it advisable or effective to use sensors? Will the vibration affect their accuracy or performance?
Okay, so this is where it brings us to again the same discussion, the data interpretation. Sensors alone will not tell us much. That's why engineering knowledge is important. Okay, so you can put many sensors, but sensors by themselves don't tell us much. So we have to interpret the data. So we have to put different kind of sensors simultaneously and create the data interpretation module in a way that whatever we need to extract, we can extract. Okay, for example, if there are two things interfering with each other, vibration as well as different loading conditions, then we can have complementary sensing systems. And then we need to have a data interpretation module to separate the data, okay, so that we can isolate their effects. Much like the HST model I was talking about in a dam.
Yes, sir. Yes, sir.
Yeah.
Mr. Dharmik Rathore asked, what could be the economical but accurate option for structural health monitoring in India?
Well, there are a lot of options, there is, as I said, even if we put a lot of sophisticated instrumentation for structural health monitoring, for the overall cost of the structure, it is very small, very, very small. Okay. But for older structures, where the structure is already in service for many years. You want to make sure they are in good shape. The instrumentation system or structural health monitoring system could be very basic to very sophisticated. It's the engineers can decide based on the budget available what is the basic. For example, in this bridge, you can just put one accelerometer. Okay, that will still give you some important data, which will be very basic and will capture only one mode, perhaps. Okay, but if you put 10 accelerometers, it will give you a better resolution in terms of its mode shapes and frequencies. So like that, you can scale up or scale down, but any kind of instrumentation and monitoring is good. It will give you some information which otherwise you cannot get.
Yes, sir. Mr. Amol asked, what is the design life of sensors and DAQ? Our contract mentions the design life of a minimum of 25 years. It is a bridge project.
Okay. Typically, if you use the electrical sensors, like, strain gauges, electrical accelerometers, those kind of systems, their life is not very long. It won't last for 20 years. If you use fiber optic based systems, they will last for 20 years. Data acquisition system, if they are well protected, they could last long because they are in protected environment. So most of the times, if you are building instrumentation for 20 years, then you have to ask the suppliers that they are well tested for outdoor environment, for their longevity, for their durability. Okay. But ordinary sensors will not last that long.
Yes, sir. Thank you, sir. Mr. Kamal Parekh asked, what to do while repair and retrofitting fire damaged RCC concrete, as no established monitoring system available?
Well, that's what I'm saying. For monitoring, there is no code or there is no. There are many guidelines, but there is no established code because it's difficult to codify these processes because they are still developing. But engineering intuition is the key here. So if you are retrofitting a structure, for example, if you take a simple beam, simply supported beam, which is in operation for 10 years or 15 years, that means it has extensive cracks and all these things, and it has settled in terms of its behavior. Then suddenly it started developing some problems because of corrosion in steel reinforcement, etc. And you want to improve its flexural capacity. So one way to improve the flexural capacity is to provide an external flexural reinforcement. It could be external steel bars at the bottom of the beams, or it could be external steel, FRP plates or FRP strips. FRP means fiber reinforced polymer, which are currently being used in civil engineering structures in many places. So, but then you need to monitor its vibration as well as displacement, okay, or strains at different points. Typical locations are the mid spans, okay. So these are based on engineering intuition. You don't need a guideline for that. But
Yes, sir. Thank you,
guideline
sir.
is good if there is guideline.
Yes, sir. Thank you,
Yes,
sir.
thanks.
Mr. Ravi Ranade asked, does any international standard specify the maximum limiting values for velocity, acceleration, and displacement for various structures like multi-story buildings, bridges, or stake structures?
As far as I know, there is none, but I could be wrong. So if you find out, please let me know.
Yes, sir. Thank you, sir. Mr. Ishan Krishna asked, during modeling, how to model the material properties since they are degraded. Also, NDT techniques does not give correct results.
Sorry, can you repeat the question?
Yes, sir. During modeling, how to model the material properties since they are degraded. Also, NDT techniques does not give correct results.
Absolutely. So that's why I said when you build a finite element model or any kind of structural model, the outcome of that may not exactly match the the behavior or response you get from the testing. Okay, so that means the material models or material parameters that you used in your model or the geometric parameters, boundary conditions, etc., may not be exactly matching. So that's why you need some updating of the models. Now, if we look at the degraded structure, uh, then you have to use different degradation model in concrete. There are many degradation model. So one of the assumption is that the concrete for the initial period, there is no degradation for say 10 years. Then after 10 years, it degrades in a parabolic fashion or in a straight line fashion. So that in another 10 years, it loses 50% of its strength or something. Okay. So there are many models available in the literature. So you can apply one of those models to calculate the reduced strength in the material and put it in your finite element model.
Yes, so thank you, sir. Professor Mahesh Tandon said that
Yeah.
steel-free deck slabs in bridges designed by Bedar,
Yeah.
Bakht, and Jagger, are any of them still in service?
Yes, yes, many of them are in service. There is a couple of them in Manitoba. There are some in Newfoundland. I think 7 or 8 bridges were constructed. They're all operational.
Yes, so thank you, sir. Mr. Radhakrishnan asked, in Indian Railway, the population of concrete bridges are much more and span varies from 12 meter to 50 meter. How to group and select representative samples on safety and economic consideration?
Sorry, I missed the first part. Can you repeat this?
Yeah, in Indian Railway, the population of concrete girder bridges are much more and span varies from 12 meter to 50 meter.
Okay.
How to group and select representative samples on safety and economic consideration?
I'm not sure how to answer this. If span plays an important role in any kind of girders, right? So, I mean,
Yes, yes.
I don't know currently how they are correct. I mean, classified in Indian context. But for example, we normally say short span, medium span, and long span bridges, right? They have different characteristics, and so very short span bridges typically are within say 20 meter or so. If you are looking at regular concrete girders, reinforced concrete girders, beyond 20 meters, it becomes not viable, unviable. Then you have to go with pre-stressed concrete girders.
Yes, thank you, sir. Mr. Ayush Chauhan asked, is any cost-effective method is available to locate defect in hidden side of steel design? Sorry, steel beam.
Steel beams defect could be of many types, right? So it could be um, if you talk to mechanical engineers, they many a times they use a lot of steel components. So they have a lot of NDT techniques like ultrasonic test, X-rays, things like that. So we could do that. We could do tap testing, vibration testing, those kind of things. But they are all localized kind of testing, except the vibration testing.
Yes, sir. Thank you, sir. Mr. Lukesh asked how to address baseline issues in sensor-based monitoring system.
Okay, as I said, that baseline depends on where you start. So if you start at the time of construction, then as soon as your structure is commissioned, the measurement taken at that point could be used as a baseline. But if you are looking at an existing structure which is already in service for several years, then whenever you start your instrumentation and data collection, you start that as a baseline.
Thank you, sir. Ms. Shivani asked how to decide data based on vibration or vibration-based method is useful for the concerned structure.
Okay, so there are a lot of discussion and lot of papers you will find on vibration-based monitoring and vibration-based damage detection. And most of them will at the end conclude that vibration-based techniques are very good in terms of capturing the global behavior of the structure, but they are not very good in terms of pinpointing the local damages or local defects. So if you take that to consideration, then my suggestion is to go with hybrid methods, means vibration-based as well as local methods. So vibration-based method can help you localize the general area of the problem, and then you go with localized testing in terms of like local methods, ultrasonic test, X-ray, etc., to know the local defects. Or
Yeah, thank
if you know the general area of the problem, you instrument that area in a more dense way to do all other measurements due to static and dynamic loads. Okay.
Yeah, so thank you, sir. Yeah, Mr. Yogesh asked, please suggest any international guideline or literature for structural health monitoring, which is widely accepted in industry.
Well, as I said, there are quite a few guidelines available from, say, Canada, US, and Europe, and also Japan. Okay, just Japan Society of Civil Engineering has published something. In Canada, ICIS Canada Research Network has something, and also in the US Federal Highway Administration has a long-term monitoring program. They call long-term bridge monitoring program. They publish some guidelines. So these guidelines are to help engineers deal with the instrumentation and monitoring issues to some extent. I think China also recently published guideline or standard on structural health monitoring.
So thank you, sir. Mr. Akash Gadvi asked, can we predict actual remaining life of a structure through any software or analysis?
Okay. The answer is yes and no. If you could monitor a structure for a period of time and build a model of the structure with high fidelity. High fidelity means you have calibrated the structure or updated the structural model as I discussed earlier, with experimental data from the field and updated it on an ongoing basis for a few years, then you have a high fidelity model. And through that model, you can track the degradation pattern. Say, for example, you updated the model this year. And then next year, whatever the measurement data is coming, you compare with this model and see what has changed. And update the model based on the new information. And you keep going this way, you can track the degradation pattern in the structure. That can help you predict the remaining service life.
Yes, sir. Thank you,
But-
sir. Mr.
Yeah, go ahead.
Yeah, Mr. Rahul Maru asks, you have mentioned about damage model in your speech. I want to understand how to integrate damage detection with material degradation and in model, and to what extent material to be degraded in model element.
Well, the degradation of materials happen mostly naturally, right? Because any material has a natural tendency to interact with the environmental factors, and that will degrade the materials. So concrete degrades in a certain way, steel elements degrade in a certain way, okay? So you have to capture the degradation pattern. So there are in the literature, you will see there are standard curves to show that in so many years, so much degradation will happen in concrete, for example. You can go with that, but there is so much of variation from structure to structure, and materials constructed with different kind of ingredients. So that's why structural health monitoring can give you an additional input to fine tune those degradation models.
Yeah,
For
thank you, sir.
example, if a literature says that concrete in 20 years will lose its 25% of its strength, let's say. But in a particular structure, through monitoring, you establish that no, it is not 25%, it lost 35%. So then you can fine tune your finite element model accordingly, and then calculate the remaining service life. Okay.
Yes, thank you, sir. Mr. Lukesh asks, what advancements in sensor technology are most promising for developing monitoring techniques that can reliably bridge the gap between early stage local damage detection and also global behavior?
Well, sensing technology is developing very rapidly. It's like computers are developing rapidly, right? So the kind of sensors you saw 10 years ago, now they are much more sophisticated. But one thing we need to remember is that with one aspect is the sensors and its accuracy and its sophistication. Other is what is the overall structural behavior that we want to capture, and where we put those sensors, and how we interpret the data. Sometimes even a basic sensor can give you very valuable information, okay? So I would say whatever available sensors are there, they're all promising. That there is no doubt about that. It is the implementation. That is where we need to focus on implementation and interpretation of data. The fiber optic sensors are great, where they are durable, they are very accurate, but there are some applications, they may be expensive. Then we go with wireless sensors, okay? So they have their own applications depending on what is the type of structure, what we want to do in terms of measurements. They're specific.
Yes, thank you, sir. Mr. Tulsi, I think so, asked, what is the best analytical method that can be used to measure or build step frame structure on mountain terrain building?
What is the best analysis technique?
Yeah, analytical method that can be used to measure or build step frame structure.
Well, I think regular structural analysis softwares will help you build the model and analyze them.
So thank you, sir.
I'm not sure if I got the question right, but any robust structural analysis software or method you can use.
Yeah. Thank you, sir. Professor Mahestrandan asked, remaining service life calculation. Any
Yeah.
simple approx method or guidelines?
Yeah, I think there are lots of seminal papers by Dan Frangopol from Lehigh University. So he proposed many degradation model in concrete. So if you go with any of the degradation model, not just that, typically concrete degrades in a way that, say, as I gave you the example, say in 20 years, it loses 25% of its strength. If you can assume it linearly changing or changing in a parabolic way. So then you will see that when that curve reaches the level where your service load can no longer be sustained, that is the time you can decide the structure is not functioning at all. Either you reduce the load or demolish the structure or rebuild. But no structure, we don't allow the structure to go to that level. Before that, we repair and retrofit. We bring the capacity a little bit up so that then degradation starts from that point and then goes to the next level. I don't know if I can show it, illustrate it on the screen. Just let me try. Let's try to draw something with mouse. So, for example, this is time, and this is say the concrete strength. Let's say S. So, and this is the original strength of the concrete. But over the time, it reduces its strength, goes like this. Now, suppose you build a structure. Typically, there are load factor, resistance factor, and all these things. Because of that, if this is your service load requirement, then you can allow the structure to degrade up to this point. But beyond that, it will not be able to function, right? So as long as we are at certain level of degradation, we could repair the structure and say we repair the structure here, retrofit the structure, and bring the level up to this point. And the degradation again starts from this, and our service life increases. So this is how we can deal with the service life prediction and enhancement of service life. But what is important here, if we can extend the service life even for a limited period of time, it gives us enormous cost saving in terms of replacement of this infrastructure. Okay.
Yes, thank you, sir. Mr. Asmit asked, what is your opinion on satellite-based SHM?
There are a lot of work done on satellite-based SHM. Like if you get good quality satellite data with high resolution, then you can track the change in position of different markers to indicate displacement. It is primarily, used for large structures like a long span bridge. You want to track the midpoint displacement, or a dam where you want to track the overall displacement. Satellite-based monitoring could be very helpful. Satellite-based monitoring could also track other factors that affects the performance of structure. For example, water level in a dam, or the movement of different parts in a tall structure. So they are useful, but you cannot get very high resolution information from there. Wherever you need a lower resolution, that means big displacement or big movement somewhere, satellite data could be helpful.
Yes, sir. Thank you, sir. Mr. I think Tulsi asked again. Now, with the latest technology, researchers have developed the foam concrete. How is it affecting the structural element? Does it have a good results or is it lacking?
Okay, see, concrete strength primarily comes from its many factors like water cement ratio, the porosity in concrete, all kind of things, right? So if you reduce the density of concrete, obviously its strength will reduce. So many a times this kind of lightweight concrete is used for architectural components or non-structural components. If you look at high strength concrete, they are usually very dense concrete. So I don't know, it depends on your application. There needs to be appropriate tests to find out if it is, what kind of concrete is good for what kind of application.
Yes, sir. Thank you, sir. Mr. Lukesh asks, what are the current challenges in SHM you suggest for future research?
Well, challenges are many. There was one question is how long these sensors will last. So durability is one aspect. Reliability of the information we get from the SHM system is another. If the sensors are installed incorrectly, then you get incorrect information. So installation is an issue. And the most important issue is how the sensor data is interpreted for the use of structural engineers. Okay. The raw data does not say much. Unless it is put in the context of engineering, it will not tell you the appropriate things. So we need to translate the sensor information to engineering information. That is where I think there are a lot of challenges, but those are manageable challenges. I think we can focus on that. Another challenge is the environmental factors. Many a times the sensor data gets affected by temperature, humidity, etc. So we need to compensate for that. Make sure that the change in the sensor data is due to structural change, not because of the other factors. Okay.
Yes, thank you, sir. Mr. Tulsi asks again, an old structure, we cut the top part and make extension and contraction point. Does it have benefit and how?
So if I understand correctly, old structure is, can you repeat the question again?
Sir, he written that an on old structural, we cut the top part and make extension and contraction point. Does it have benefit? How? I also not
It's
understand.
difficult to respond to this question because this looks like a very special requirement.
Yes.
So obviously the consultant in on the ground will be able to assess that. I won't do it without any consideration of the structural implication. There could be benefits in terms of the usage. Many a times we repurpose the structure for its different use, right? So, but anything we do in terms of modifying a structure needs to be done professionally with professional consultation and following the current code. These structures, old structures are built on old codes, but when you do a major retrofit, it has to follow the new codes. At least
Yes, sir.
that's
Thank you,
what
sir.
we do in Canada.
Yes,
I'm sure
Yes,
in
sir.
India, similar thing happens.
Yes, sir. Yes, sir. This
Vikas?
is the last. Yes, sir. Last question, sir. Last question.
Yeah.
This is from Mr. Solomon. Could you please put the research paper name for the residual strength assessment of concrete structure?
I can send it to Mr. Dr. Dhawan later on.
Yeah, thank you, sir. Thank you, sir. Yes, sir.
Okay.
Dhawan, sir. These are the only questions.
Professor Ashutosh, we are really grateful for your experience and sharing knowledge in this new field on structural monitoring.
Thank you.
Doctors, of course, do a lot of investigation, but now in years with putting sensors, we can get good results. And then on behalf of Institution of Structural Engineers, I really thank you very much for agreeing to my request, because I gave you only a few days. You're personally grateful for your acceptance and then delivering this useful lecture on the new topic and the new emerging technology like structural health monitoring. So thank you very, very much for again for sharing your knowledge and experience to our young structural engineers in our country.
Thank you very much for the opportunity to talk to the audience here. And I'm grateful for the questions. Questions are very good. If there is some follow-up questions, you can forward them to me. I'll respond to it to the best of my ability. And I will send some of the references I was talking about to you to share with everybody.
Right, that would be great. So very, very nice of you. Thank you so much. So let us conclude.
Yeah, thank you.
Vikas, let us conclude.
Yes, sir. Yes. Thank you.